Hey everyone. Okay, now we're starting to pay things off, right? Because we've gone over the basics of what light is, how light works, what are the properties of light, because now we can start exploiting that to figure out things about stars, right? You take the light from a star, you shine it through a prism, and you get all the colors of the rainbow, but not with equal brightness, right? And whether a star is brighter at one wavelength or brighter at another wavelength depends on the temperature. And it only depends on the temperature, which is super useful, right? What color a star is only depends on the temperature. If you know what color that star gives off most intensely, you know how hot it is. From, trillions and quadrillions of miles away, we already know how hot the star is, which is a very powerful tool in astronomy. So, we got these two stars, Rosa and Obaton, right? And we've taken their spectra where we say, okay, graph the power output versus wavelength. So here's how much, not power output, energy output. Here we have a graph of, right, how much energy the star is giving off at all these different wavelengths, right? We got the visible spectrum here, which means at the, if wavelength is increasing this way, then this part of the spectrum is shorter wavelength than visible. What's shorter wavelength than visible? Ultraviolet. Here's the visible spectrum. And then longer wavelength than visible is the infrared. All right, so we've got, and then, the X-rays and all that would continue this way, but stars don't give off that much X-rays and gamma rays. They do still, right? Because a continuous spectrum, right? Any object giving off a continuous spectrum gives off light at all wavelengths. It's just that the amount of energy that a star gives off in the X-rays and the gamma rays is very, very small compared to the ultraviolet, the visible, and the infrared. So we can kind of cut it off there. And then these stars give off a lot of infrared, and they're also going to give off a little bit of microwave and radio, but so little that we're just going to cut it off unless we're really, really interested in how much microwaves or radio a star gives off, which, you'll see it in the torus lesson. But, for our purposes here, we'll stick with the big three: UV, visible, and infrared. Let's look at Rosa here, right? Rosa is brightest at what wavelength? Looks like the visible light. So if Rosa is giving off more, not visible. I saw V and thought visible. No, violet, right? The V is for violet. Right? So this star is giving off blue and violet brighter than any other color, so it's going to look bluer. Obaton is brightest in the red light, right? It's still giving off all the other colors, it's just emitting red most intensely. So if you were looking at Obaton with the naked eye, there'd be more red light going in your eye than any other color, so it would look redder. So which one is hotter? Well, right? Remember the Wien's law over here, right? Wien's law is the name for this equation. And the temperature and the peak wavelength are inversely proportional. So higher temperature must mean that it peaks at shorter wavelength. And shorter wavelength light is what color? Right? Shorter wavelength is bluer. So basically, that's the relationship for Wien's law, right? That the hotter an object is, the bluer it is, because it's only giving off blue light, but because it's brightest in the blue part of the spectrum. And then cooler objects are redder because they are brightest in the red part of the spectrum. So, which star is hotter? Gotta be the bluer one. There you go. Alright. So rather than just saying, we know that Rosa is hotter than Obaton, but how hot are we talking about? What kinds of temperatures are we talking about? Well, if you actually measure and you actually go across the spectrum and go, what specific wavelength is Rosa brightest at? Oh, okay, it's brightest at 414 nanometers. Go across the spectrum. What wavelength is Obaton brightest at? Oh, okay, it's brightest at 725 nanometers. Okay, so now that instead of just saying, oh, this one's it's bright in the violet, it's bright in the red. How violet? Well, violet as in this specific wavelength. Red as in this specific wavelength. That specific color of red, that specific wavelength of red. Then we can say, okay, well, we've got a pretty good idea that since Rosa is bluer, it must be hotter. But let's make sure that our math actually backs us up here. So let's do some math to figure out what the temperatures of these two stars actually are. And I'll pull up my spreadsheet from before because Wien's law is a super useful equation. And I'll pull that up on my screen over here, right? Wien's law over here. I'm going to add this to my equation sheet. Where what? What are we measuring? What are we actually measuring? Well, right? You're taking the spectrum, you're taking the light from that star, you're splitting it up into the spectrum, and then you're going across the spectrum and going, okay, what wavelength is brightest, right? You're measuring the peak wavelength. And then we're calculating what the temperature is based on that wavelength. So I'm going to measure the peak wavelength, and I'm going to calculate the temperature. Okay. I'll move that to make a little room. Okay. So for Rosa, the peak wavelength is 414 what? Nanometers, right? Always write down your units to keep track for yourself. And then if we use Wien's law over here, then remember that Wien's law gives us the temperature in Kelvin. Gives us the temperature in Kelvin when we put the peak wavelength in units of nanometers. So how do we calculate the temperature? The temperature equals 2.9 times 10 to the 6, which of course I'll just put 2.9 E6 divided by the peak wavelength. What's the peak wavelength? It's whatever number I put into cell B6. So okay, so I have my spreadsheet programmed to go grab the peak wavelength in B6 and do 2.9 times 10 to the 6 divided by that, and therefore Rosa must be 7,004 Kelvin. Or, 7,005 if we're rounding up. Okay. So Rosa must be 7,005. I'll just round it to the nearest degree Kelvin. Okay. So what's the temperature of Obaton? Well, Obaton has a peak wavelength of 725 nanometers. An even 4,000. Okay. Did this match our prediction? Which star did we think was hotter? Rosa. Which star did we calculate was hotter? Rosa. Okay, good. Always good when your math agrees with your prediction, with your expectation. Okay. So, how about talking about Rosa and Gianfar? All right. Which one peaks at the longer wavelength? Well, Rosa peaks at the violet. Gianfar peaks in the violet. So they peak at the same wavelength. If they peak at the same wavelength, what's the relationship of their temperatures? Well, the peak wavelength only depends on temperature, right? The peak wavelength for a continuous spectrum only depends on the temperature. So if these two stars peak at the same wavelength, then they must have the same temperature. Which one appears redder? Well, they're both giving off the blue and the violet light most intensely. Neither of them is like brightest in the red or anywhere close to the red. So which one looks redder? Neither. Which one looks bluer? Both. Which one has the greater energy output? Okay, what's another word for energy output? When you're talking about the energy output of a star, when you're talking about how much energy a star gives off, in total every second. What's another word for that? Luminosity, right? So the luminosity, if you want to get the total luminosity of the star, when you have the spectrum like this, like I said in the lecture video, right? You can get the luminosity. The luminosity is just the area under the curve. Right? Look at the area under the curve. Add up how much energy the star gives off at every wavelength. Add that all up, and you'll have the total luminosity. So which of these two stars has the greater area under the curve? Well, Rosa's area is bigger. The area under the curve for Rosa is bigger than the area under Gianfar, so Rosa must be the higher luminosity star. All right, how about Rosa and Sortho? Which one peaks at the longer wavelength? Well, longer wavelength increases to the right. So which one peaks further to the right? Sortho. Right? Rosa is bluer. Sortho peaks here in the red, right? Sortho peaks here in the red. So which one has the lower temperature? The lower temperature is going to be the redder star, which is going to be Sortho. Which one looks reddest? Sortho. Which one looks bluest? Rosa. Which one has the greater energy output? Well, which star has the greater area under the curve, right? Rosa has this area under the curve. Sortho has this area under the curve. Try to do this in a different direction here. Which one has the greater area under the curve? Looks like Sortho. Right? Sortho is giving off more light. Sortho has a higher luminosity, even though it's cooler. How can that be? How can it be that Rosa and Gianfar have the same temperature, but Rosa is brighter? Well, think about a star, right? A star is spherical, right? A star is a sphere, and that light is coming off the surface, right? That light is being emitted off the surface of that star. So how much light the star can give off in a second, in other words, its luminosity, depends on what? Well, it depends on the temperature of the surface, right? The hotter the surface is, the more light it can give off per second. But also the size of the star, right? If that star is bigger, if that star has a larger radius, then it has a larger surface area. And if that star has a larger surface area, then it can let more light out per second. And if it's giving off more light per second, it's going to have a higher luminosity. So how is it possible that Rosa is giving off more light per second than Gianfar, even though they have the same temperature? Rosa must be larger. Rosa must have a larger radius, a larger surface, to let more light out. How can it be that Sortho has a lot higher luminosity? I mean, this area looks considerably larger than the area under Rosa. How can Sortho have a higher luminosity than Rosa does, even though Rosa is hotter? Wouldn't the hotter star be brighter? Well, Sortho must have a much larger radius. It must have a much larger surface area so that it can let a hell of a lot more light out, pardon my French, a heck of a lot more light out per second, even though it's cooler. This is why these stars are called red giants, right? Sortho is a red giant. It's red because it's brightest in the red. Why is it brighter in the red? Because it's cooler. So Sortho is red because it's cool, but it's giant. It's so much bigger than Rosa is that it can let more light out through that much larger surface, even though that surface is cooler. So these, stars like Sortho are called red giants because they're red and they're giant. They've got these really high luminosities, even if they're cool and red. So now, we'll pick this up with the next lesson, but this is the awesome thing. This is the awesome thing about studying stars is that, to go to our spreadsheet here, right? If you know the luminosity and the temperature, right? The luminosity of a star, how much light that star can emit per second, depends on how hot the star is and how big the star is. So, if we know the luminosity and the temperature, then you can say, well, how big must this star be? How big must this star be if it's letting off this much light from a surface this big? From a surface this hot. How much big must it be? Knowing the temperature and the luminosity, how big must this star be? And now we can figure out a third thing about the star. We can figure out how big it is, what its radius is. We know Sortho must have a much larger radius so that it can be this bright even though it's not very hot. So now we figured out another thing about the stars. We got the luminosity with the temperature, and now we got the size. And that'll help us shortly. All right, but I'm getting ahead of myself, right? Let's say, all right, you've got this first star here. This first star has a peak wavelength of, it looks like 500 nanometers. So, what type of light is that? Let's go here. What type of light is 500 nanometers? Well, remember, I said before, it's handy to remember that visible light goes from between 400 nanometers, so this is 4, 5, 6, 7, 750. So, visible light goes from 400 to 750 nanometers, right? Here's the violet end of the visible spectrum. Here's the red end of the visible spectrum. So, if this star is peaking at 500 nanometers, that's in the visible spectrum. All right. How hot is that? Let's let our spreadsheet do the math for us. If that star is peaking at 500 nanometers, then that star is 5,800 Kelvin. Oops. There we go. So, 5,800 Kelvin. This star here is peaking at what? It looks like that's... if that's 1,000 Kelvin, okay, 1,900, 850? Sounds good. All right. So if this is 500... that's 500. So 4, 5, 6, 7, 750. All right. So here's the visible spectrum, which means all of this is longer wavelength than visible, which means this star must be peaking in the infrared. Right? And everything over here must be ultraviolet. So to the right of the red light right there, that's all infrared. So this star is giving off infrared light most intensely. Why? Well, if it's giving off longer wavelength light, if it's redder, it must be cooler. So whatever the temperature of this star is, it's got to be cooler than this first star because it's peaking at a longer, redder wavelength. So whatever temperature we get, we expect it should be cooler, but let's check our work here. What does this look like again? What did I say? 8. Let's see, if this is 750, 800, if this is 800 and that's 900, 825? Let's say 825. If you said 800 or 850, I think anything in that range is pretty reasonable. But I'm going to say 825. All right. So that star has a peak wavelength of 825 nanometers, 3,515 Kelvin. So 3,515 Kelvin. Always write down your units, right? So we expected that this star should be cooler than the first star, and that's what the math says. Great. When the math matches our expectations, got a pretty good idea that we're getting the right answers. Okay. All right. Well, now where do we go? Right? Well, where we go is where I was leading you to earlier, right? Now that we've got a spreadsheet that gives us, right? All we've got to do is do these three measurements, parallax, flux, peak wavelength. All we've got to do is have these three measurements, and we can figure out the distance of the star, its luminosity, its temperature. And now, if we know luminosity and temperature, now we can figure out the size of the star, or specifically the radius, since it's a sphere. So, how do we do that? That'll be the next thing. All right. Pick it up from there. All right. Bye, folks.